Investigation 2-3, we're going to do a flip lesson, and we're going to start with this handshake problem. And then I have a few examples for you to work along with me. So if you want to take notes on this, you can go to the Google Classroom page and select this link, and there should be a worksheet in your assigned to you that you could follow along with. And so if you need to do that, I would just pause the video and open up the worksheet. It looks, whoops. It looks a lot like the Smart File. Here it is. And you could just kind of record your work on this worksheet. It's just an option in case you're interested. So if you could read the handshake problem there, and I'll read it too. We're not actually going to solve this problem first, but the goal at the end of the day would be able to solve a problem like this using a model and observing patterns. So we'll start with it and then do some simpler problems first. So you'll also find this on page 108 and 109 in your book. But the handshake problem's famous, and if you're at a party, for example, there's 30 people, and everybody shakes hands with everybody else one time, the question is, how many handshakes were there all together? And like we talked about earlier today, when you do a problem like this, you always want to model it instead of trying to figure it out for 30 people. So if there's one person represented by a dot, we'd just draw that diagram. And if there were two people, our model would just be like this. And so we see with one person, there's no shakes, because you don't shake hands with yourself, but for two people, there's one shake. And that line segment indicates the shake. And if there's three people, then we'd have the dots representing the three people, and therefore we'd have three shakes. And then if there's four people, the model would look, so I always just arrange my dots like in a kind of a circular pattern, or eventually it would be a circular pattern. Like for 5 people, it'd be like a pentagon. So if there's 4 people, there'd be these shakes, like that first person shakes with all 3 people, and the next person just shakes with those 2 people, and the last person shakes with that person. So there's 6 shakes here. And that's what goes under there. So we're going to come back to this problem, and it may be that this is where we start class tomorrow, but to solve this problem, we want to do a few more basic problems. So the next couple of problems I have on that sheet are just examples, and they're not tied into a geometric picture right now because I just want you to focus on the skill required to find a pattern. So we learned about linear patterns this week, and in order to do the linear pattern, we always look at the first difference and see if we have a linear pattern. So the first difference here, 8 plus 7 is 15. So we're going up by 7. But then 15 plus 9 is 24. And 24 plus 11 is 35. So we look at that first difference and we say that it's not constant. In other words, it's not going up by the same number over and over and over. So if it's not constant, then we don't have a linear pattern. So first difference isn't constant, so we don't have a linear pattern. So we can't use the quick, easy technique from yesterday. Move this over here. So what we have to do is we have to look at the second difference instead. So the second difference would be the difference of the first difference. So in other words, from 7 to 9 we go up by 2, and from 9 to 11 we go up by 2. So maybe we need to back up a little bit and just think about what this value would be for the fifth term. We'd have to add 13, so we'd have 48 here. And so from 11 to 13 we go up by 2. So we say the second difference is constant, and whenever that's the case, this is called a quadratic pattern. I can't make that bigger, but it's a quadratic pattern. So that means in here, if you think way back to algebra last year, one of the ways we looked at quadratics was in factored form. And so what we're going to look for are two linear patterns that are multiplied together. So for example, like 2n plus 3 times n plus 1, that's a linear pattern, and that's a linear pattern, but when you multiply them together, you get a quadratic pattern. And we're going to learn how to do that. So anytime the second difference is constant, you have a quadratic pattern, and what you're going to do is look for a multiplying pattern. So remember, at first, this is going to be a little maybe hard to understand. So just kind of take it all in, and you can ask questions tomorrow. Now that I've established that, I don't need this information anymore, so I like to draw lines through what I don't need anymore. The other thing that I'd like to do is, you really want to keep your work super organized. So I'm going to draw some straight lines here, maybe in a lighter color. So I keep my work organized with my table. Oops, well, I didn't get a lighter color, but so I'm just extending these lines. That's why there's so much space below this. And instead of using the value numbers, we're going to try to find a multiplying pattern. So what I mean by that is, instead of using 8, I'm going to find ways to get 8 in a product. So like, let me move this up here. We're looking for a multiplying pattern. And one way to find 8, I could do 1 times 8. I could do 2 times 4. So I'm just going to write those multiplying patterns below the 8. 1 times 8, 2 times 4. And then the same thing for the 15. I could do 1 times 15, 3 times 5. 24, there's lots of multiplying patterns. So the idea would be, you look at the multiplying patterns and try to find a relationship between the first number. So if I'm going from 2 to 3, could I find a multiplying pattern for 24 that starts with 4 to keep that pattern? So now the first number is, I'm going from 2 to 3 to 4, and I could do 4 times 6. So if that works, then I want to check and see, does the second number also fit a pattern from 4 to 5 to 6? So So I'm going up 4 to 5, 5 to 6. So in other words, can I continue the pattern and have two numbers multiplied together where I go from 2 to 3 to 4 to 5 and look back up at this term here, 5 times 7 is 35. So I've just taken these numbers here, I'm going to cross them out, and instead of using those numbers, I'm going to use the pattern established with their product. So again, remember, this is confusing at first, but this factor here is going to be the pattern for the numbers in the green box. And this factor here is going to be the numbers in the blue circles. So if I look at the numbers in the green box, to get from 2 to 3 to 4 to 5, I just have an increase of 1. So I'm going to write 1 in, just like we did in investigation 2. And then I have to go all the way to the top here. And if I say 1 times 3 is 3, but my goal was really to get 4 way down here, I have to add 1. If I try that again over here, 1 times 4 is 4, but my goal is to get this 5 here, I still have to add 1. So my rule is 1n plus 1. So just to clarify, if I'm the 5th term, down here, if I follow my pattern, I would really have 6 times 8 is 48, and the 6 follows the pattern from 5 to 6. So 1 times 5 is 5, but to get to 6, I have to add 1. And now I'm going to do the same thing over here. To get from 4 to 5, 5 to 6, and 6 to 7, I go up by 1. So that's 1n. But now I have to adjust my value. So 1 times 4 is 4, but now I want what's in the blue circle. I need a 7, so I have to add 3. Well, let's check my work. 1 times 3 is 3, but now I need a 6, so adding 3 works. So my rule is n plus 1 times n plus 3. And to check my work, I can plug in n equals 5, and I would get 5 plus 1 times 5 plus 3, which is 6 times 8, which is 48. So it works. So I'm going to do one more example, and then I'm going to stop the video, and you guys are going to come back to class and practice, and we'll do the handshake problem together. So there's a lot of steps. The first step is check the first difference. So from here to here, I go up by 13, and then from here to here, I go up by 25, and then from here to here, if I do 77, take away 40, I go up by 37. So if you don't know where I'm getting those numbers, 40, take away 15. If I borrow here, that's where the 25 came from. So my first difference is not constant. So my second difference 13 plus 12 and 25 plus 12. My second difference is constant. That tells me we have a quadratic pattern. So that means over here we have a linear times a linear. Once I figure that information out, I don't need these numbers anymore. So I'm just going to cross out the numbers. I've used them, that's all I need. So my next step is to make my table nice and organized, extend the lines. So I keep all my numbers in order. And then I look for a multiplying pattern. So remember that let's see. I'll go with green. So now what I'm going to do is I'm trying to look for a multiplying pattern. And this is one of the harder tasks. So to get 2, I can do 1 times 2. Not a lot of choices there. So maybe 3 times 5. So if I went from 1 to 3, is it possible that I could do 5 times something to get 40? And I can do 5 times 8. So 1, 3, 5, 7. And then 7 times 11 gives me 77. So I've established a multiplying pattern. And I like to separate them into 2 groups. So the second number will be my second factor, and the first number will be my first factor. So now I'm not going to use these numbers anymore. I'm going to use the multiplying pattern. So to get from 1 to 3 to 5 to 7, I go up by 2. So this is 2n. And then I have to check my adjustment. So 2 times 4 is 8, but I need a 7, so I have to subtract 1. I'll check it here. 2 times 3 is 6, but I need a 5, so subtract 1 and that works. I do the same thing for the next term. To go from 2 to 5 and 5 to 8 and 8 to 11, I'm going up by 3. So that's 3n. So erase this. So I'm going to make my adjustment. 3 times 4 is 12, but I need 11. So I should have to subtract 1 if I've done this right. Let's test over there. 3 times 2 is 6. I need a 5. And so subtracting 1 works. So that's my rule. I can do a check. If n is 3, it'd be 2 times 3 minus 1 times 3 times 3 minus 1, which is 5 times 8, which is 40. And that's correct. All right. That's a little longer than I thought, but I think enough for you guys to come back and practice. So that's where we'll stop.